Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And as I do every Saturday, I'm featuring another biography of a famous mathematician. And this is one of the greatest ones of all time, without any doubt. Isaac Newton. I'm sure you guys have all heard of him. He lived from 1642 to 1727. Some people say he was born in 1643. We hadn't switched to the Gregorian calendar yet, but if we had, he would have been born on January 4th, 1643. But according to the calendar that was being used at the time, he was born on Christmas Day in 1642. A little piece of interesting trivia, I think. Anyway, here's the bio I feature of him in my book, and I've got a whole page. Most of my bios are only half a page. I have a whole page devoted to, I think, two or three different mathematicians, including Newton. Leibniz as well. Leibniz was another great one. They both invented calculus independently of each other. But Newton had an amazing number of accomplishments. I think any one of which would have made him famous. But anyway, so what did Newton do exactly? Well, I'm going to start at the beginning. Newton, this is where Newton grew up, or at least where he was living when he made his greatest discoveries. This is in Woolsthorpe, England. This is the house he grew up in. I don't know if it's the house he was born in, but it's the house he was growing up in. And he lived in this house when he had his kind of miracle years from 1665 to 1667. This is when he made his greatest discoveries and where he made them. And this was during the Black Plague in England. The school was closed. I think he was teaching at Cambridge University, but they closed down the university due to the plague, so he had to go home. And this is where he did his greatest work. And so what did he do at home? Well, the first thing he did, or one of the first things he did, was he discovered the spectrum of light. I think you guys are all familiar with this experiment. He had a triangular prism, and he took, what usually is called a pencil of light, a little sliver of light, probably from the sun, through a hole. He had light going through a small hole, and then he had an incident on a triangular prism. And what happens, this picture is exaggerated quite a bit, but what happens is first the light gets refracted, it bends when it hits the surface, the surface on the left here. But not only does it bend, but it turns out the amount by which the light bends depends on its color. Red light bends the least and violet light bends the most. And he observed this with this prism. And he was actually able to break up white light into the familiar spectrum, which looks like a rainbow. And actually, rainbows kind of follow the same law. But here's a picture of him, a diagram of him demonstrating the spectrum of light. This was a really revolutionary discovery. I mean, before Newton, I think everybody thought that white light was pure light. Newton actually demonstrated that white light was not pure light. In fact, it was a mixture of all other colors of the spectrum. Each color was pure. You couldn't break down the colors anymore. He demonstrated that as well. But anyway, that was I think, his first really great accomplishment. And also, there's this kind of apocryphal tale that he was sitting under the orchard. He was sitting in his orchard one day, and he observed an apple falling. The apocryphal tale is it fell on his head. I don't think it fell on its head. I think it just fell on the ground, and he observed it falling. But being the genius that he was, he thought about what made the apple fall. I mean, we all know about gravity. We all know that apples fall. People have been knowing this since primitive times. Anything you drop will fall. That's obvious. But he was trying to ask himself, well, what's the mechanism by which the apple falls? I mean, Galileo had done some experiments involving falling bodies. He actually discovered, the law of, the law of falling bodies. F equals mg, or acceleration equals g. where g is the gravitation, the acceleration due to gravity of the Earth. I think I went over that law when I was talking about Galileo, but Newton actually did a lot more. Newton, then he was thinking about, well, what keeps the moon in orbit? Is it the same force? I think he was the first person to ask this question, whether it was the same force that made apples fall on Earth. That's what we usually call gravity on Earth, terrestrial gravity. Was that the same force that kept the moon in orbit around the Earth? Then, being the brilliant, mathematician and scientist that he was, he realized that the moon is in fact falling due to the gravity of the Earth. And well, you might ask yourself, well, why doesn't it hit the Earth if it's falling? Well, it's falling in a circle. It's accelerating. That's called centripetal acceleration. It's falling, but it never hits the ground because it's falling in a circle. That's Anyway. I'm not going to go into that here. I do that in other videos, but he reasoned, and he came up with. Here's what he came up with. I think he knew roughly how far the moon was, and he was able to calculate the acceleration of the moon, the centripetal acceleration of the moon to the Earth's gravity. And what he discovered was it obeyed this law here. This is Newton's law of universal gravitation. Really amazing. I think one of the greatest equations in all of physics, the law of gravity. Um, I mean, this stood for over 200 years. Finally, it got modified, not replaced, but it got modified by general relativity due to Albert Einstein. That would have to wait until 1915, the early 20th century. But Newton came up with this law, I think, in 1666. He didn't publish it until 1687. I'll get into that later. But so what this law says is that any two massive objects in the universe, and usually it's easier to think about stars or planets, big objects, they exert a gravitational force on each other, and the equal and opposite forces. That's a consequence of Newton's third law of motion, which I'll get to in a minute. But the magnitude of these forces, F1 and F2, they're both equal magnitude, and their magnitude is equal to a constant which we call capital G. This is the universal gravitational constant. Sometimes people just call it Newton's gravitational constant. Its numerical value is 6.67 times 10 to the minus 11 meters cubed per kilogram second squared, in case you're interested in SI units. And so you take that constant and then you multiply by the product of the masses, M1 and M2, and then you divide the whole thing by the square of the distance. And of course, we're assuming these are point objects. If they're not point objects, you have to integrate over the whole thing. I think that was a big reason Newton didn't publish this theory right away, because it turned out, since the Earth is spherically symmetric, it turns out that you can actually prove using calculus that a spherically symmetric mass obeys as if all of its mass is concentrated to center. At least from outside it does. And so if we made the simplifying assumption that the Earth was a point mass, then it would obey this law, and the moon too. And that would predict the observed acceleration of the moon, centripetal acceleration. Pretty amazing. And not only did he come up with the law of universal gravitation, but he came up with these three laws of motion. Together, Newton's three laws of motion plus his law of universal gravitation are what's usually called classical mechanics. And that stood the test of time for about 250 years. This basically was just about all of physics that was known until Einstein. Of course, we learned about electricity and magnetism later, so that kind of added to physics. But Newton's laws stood the test of time. His laws of motion and his law of universal gravitation. And they're still very good approximation. I mean, for most practical purposes, they work just fine. It's just when you deal with things that are moving close to the speed of light, or you're dealing with really huge things, like black holes or galaxies, that's when you have to modify your theory and use, Einstein's theory of relativity. But Anyway, so what are Newton's laws of motion? Well, there's three of them, and they're all pretty easy to state. First law, I think this one was actually discovered by Galileo. Um, this is the law of inertia. This says that if any object at rest will remain at rest, or any object in motion will remain at motion with the same velocity, in other words, the same speed and direction, unless it's acted on by an outside force. And so it doesn't require force if you neglect friction. And this is kind of counterintuitive. This isn't what the ancient Greeks believed, by the way, like Aristotle. I think in ancient Greece they believed that the natural state of everything in the universe was to be at rest. Everything was going to come to rest. That seems what happens, but the reason why it seems that way is because of friction. If there were no friction, just imagine you're playing like air hockey or something. If you had a hockey puck moving on a cushion of air where there's essentially no friction, it's going to keep moving at the same speed, the same direction forever. I mean, obviously the court's going to be finite size; it'll just move across the court, but it won't slow down. I actually used air tracks when I was studying physics as an undergrad. Maybe some of you guys have too. You have these little air tracks, and you put these cars on the air tracks, and there's essentially no friction. They keep moving at the same speed, and it's one-dimensional, so they don't really have a choice about what direction. Anyway, that's Newton's first law. And then his second law, I think this is the one that's best known. This is F equals ma. This says what happens if you do act on a massive object with a force. It causes it to accelerate. And the acceleration is proportional to force and inversely proportional to mass. The more massive it is, the less it accelerates. And then the third law is the law of reaction. This says for every action, there's an equal and opposite reaction. This is really just a consequence of the conservation of linear momentum. And they showed two skaters here. You can demonstrate this by skating. I've usually seen it with ice skating, but imagine you have two roller skaters or ice skaters, and they push each other. Well, they're both going to move in opposite directions at the same speed because they both pushed each other with the same equal and opposite force. Their initial momentum was zero, so their final momentum added together is zero. That means they have to have equal and opposite momentum. Anyway, those are Newton's three laws of motion. That comprises, along with his theory of gravity, that comprises everything that was known about mechanics for about 250 years. Pretty amazing. And also, another thing that's really amazing about this, I can't say enough about this, because, I used to study physics. So I'm really fascinated by all this stuff. But, we were kind of learning some of the consequences of Newton's laws a long time before Newton. As a matter of fact, Galileo, like I mentioned, he basically discovered Newton's first law. He discovered the law of falling bodies, which is a consequence of this law of universal gravitation. It also turns out Kepler's laws of planetary motion you could derive all of those from Newton's laws of universal gravitation. So pretty much everything that everybody had discovered about mechanics during the scientific revolution was provable using Newton's laws, which I think is really, really amazing. In my mind, I think he was the greatest physicist of all time. A lot of people debate this, but I think he was even a greater physicist than Einstein. They're a little hard to compare, but they were probably the two greatest. Some people think Einstein was greater. I actually think Newton was a little bit greater. Maybe just because his theories have stood the test of time and they're still really good approximations to what's really going on. But anyway. And then what else did he do? Oh, yeah. And I think one of his greatest, and so far I haven't really been talking about math. And he was also a really great mathematician. He was mostly known as being what I said is probably the greatest physicist of all time. But he was probably, I think in my opinion, I don't think he was the greatest mathematician of all time. But he's definitely in the top five, I'd say. I think maybe Gauss and Euler were a little greater mathematicians than him. They were probably the two greatest. But Newton, and then if I was going to finish the top five, I'd probably have to say Archimedes and Ramanujan. I mean, those are just who I consider the five greatest mathematicians of all time. You may disagree, I don't know. But anyway, so what did Newton do? What was Newton's really, tour de force in math was his invention of calculus. He had to invent calculus in order to prove his universal law of gravity. The reason he invented calculus was in order to be able to prove that the Earth acted as if all its mass was concentrated in its center. You can actually prove that using integral calculus. It's pretty complicated. I've done it though. And so there's two types of calculus, and I'm going to get to calculus in volume 2. There's differential calculus. That's what you usually first learn. That deals with rates of change, how fast functions are changing. That deals with things like speed, velocity, and acceleration. And then there's integration, which turns out to be the opposite of differentiation. It seems like a completely different problem, but integration involves calculating areas under curves. Areas are volumes, like areas of curve under curves or volumes of surfaces. And you can do a lot of other things with integral calculus too, like calculating arc lengths. That's a lot harder, but anyway, those are the two kind of most basic types of calculus. And Newton invented it. And Leibniz did too, in all fairness. Newton invented calculus, I believe, around 1665 or 1666. I don't even know if people know the exact year when he came up with calculus, but it was about 10 years before Leibniz. Leibniz came up with it independently. They lived in different places. Newton lived in England, Leibniz lived in Germany. And most people consider Leibniz's version of calculus superior to Newton's. They basically prove the same laws. It's just that Leibniz's notation was a lot clearer, and that's why most people use Leibniz's notation rather than Newton's. Newton's used a prime notation. I think he used dots. Nowadays we use primes for derivatives. He gave calculus a different name, by the way. He called it fluxions. Leibniz had the DDX notation. But anyway, so I'm going to get into calculus probably. I don't know when I'm going to get to that, but it might be another year or so. We'll have to see how it goes with my lessons in the Math Lovers book. But it starts around, I think, chapter 12 or 13 in volume 2. Anyway, we'll get to this at some point. And most people don't learn calculus until like maybe the first year of college. People go to STEM. It's pretty rare that people learn calculus in high school. But anyway, yeah, I did. I learned calculus my senior year of high school, but I was always pretty advanced in math, so don't need to toot my own horn too much. I am a mathematician, so. Anyway, and then Newton came up with this method. Actually, these days it's called the Newton-Raphson method. I think it's generally believed that Newton did not come up with this method. He actually stole it from one of his students. He had a student named Raphson who came up with this method, and either Newton stole it and took credit for it, or he collaborated with Raphson. Maybe he modified it a little bit. But I think nowadays it's generally believed that Newton plagiarized Raphson. And Newton was a jerk. I mean, one thing I should say about Newton, even though he was an amazing mathematician and physicist, and I think one of the smartest people that ever lived, I couldn't even guess what his IQ was. I've always imagined his IQ was probably somewhere in the mid 200s, which is probably even unmeasurable by today's standards. But he was an asshole. I mean, he was not a likable person at all. I think he had a really rough childhood, but he was not a nice person, and he had a big battle with Leibniz over who discovered calculus, even though they discovered it independently. He won that battle just because he had so much power. Basically discredited Leibniz, which I think was pretty horrible. Another thing I think he did was pretty horrible was that, excuse me, he plagiarized his student Rapson on this Newton-Raphson method. But the Newton-Raphson method is a really powerful method for estimating roots or zeros, if you like, of differentiable functions. And I have the formulas on the slide. I'm not going to go over it, but I guess one special case of the Newton-Raphson method is Hero's method for computing square roots. And this method converges extremely rapidly. I mean, you only have to do about 4 or 5 iterations. By then, you already, got your root correct to about 20 decimal places. So it's a very rapidly converging method. Um, and it's still used today. Very useful method. And it relies on calculus. And I think the only other mathematical accomplishment I know of by Newton was he came up with these identities called Newton's identities. I'm not going to go over these, but these are very useful. These allow you to calculate sums of powers of arbitrary numbers. Um, if you, um, yeah, I mean, I'm not even going to go over this, but they're very powerful identities. I've used them myself. And they're very useful. But this is not calculus. This is more like abstract algebra. It's used a lot in abstract algebra, but it's very useful. And then one other thing Newton did. Oh, yeah, he actually did a couple more things. He invented the reflecting telescope. I believe this was 1668. I already mentioned that he discovered the spectrum of light. The white light was composed of all the colors of the rainbow. Another thing he did was he invented a very useful type of telescope known as the reflecting telescope. And I believe most optical telescopes today are reflecting telescopes. They use mirrors rather than lenses. And they can be much smaller, much more compact. That's the main advantage of reflecting telescopes over refracting telescopes. Refracting telescopes have to be a lot bigger, and if they're really powerful, they involve really big lenses, and they're not so practical because you have to grind all the glass. You have to make sure that the lens is ground just perfectly, and then it's very heavy. And also it has problems with what's called aberration of light. Unless you make corrections, it'll separate the colors of light for the same reason as a prism does. But reflecting telescope doesn't have this problem. No aberration, at least no aberration of the separate colors of the spectrum. All colors get magnified equally, and then they can be much smaller. And actually, my uncle used to he had a Celestron, an 8-inch Celestron telescope that he bought in the 70s, and he used it for, we used to use it to look at various types of astronomical objects like galaxies and nebulas and all this stuff. And it was a reflecting telescope, kind of like this one, except it had a tracking motor because the objects in the sky move since the Earth's rotating about its axis. So you need a motor if you're going to look at things that are really far away. Newton didn't have one, but he was still able to look at some very distant astronomical objects with his reflecting telescope. So he was a good astronomer too. Um, and, I think I should mention the Principia Mathematica. All of it, you didn't do this for about 20 years. I said that his kind of miracle years were 1665 to 1667. That's when he came up with his greatest discoveries in Woolsthorpe during the Black Plague. But he didn't publish them for about 20 years. I don't know why he waited so long. I think part of the reason was he wanted to make sure he got everything exactly right. I think he was also a kind of a hermit, and he didn't really correspond that much, at least at first, with other people in the math or physics community. But finally, he got around to writing this really groundbreaking book called Principia Mathematica. And I've actually seen this book. It's in the at least during the 1980s, it was in the British Museum. I went to the British Museum and saw this book. They just had it open on one page and it was behind a glass, so it couldn't, thumb through the book. But this book is considered one of the greatest books ever written, and he published it in 1687. And this book contains all of classical math mechanics, basically everything he discovered about gravity and his three laws of motion. It has a lot of examples in it. The way he did things was very different from today. Today we would use algebraic derivations for most of the problems. He had a bunch of problems in this book, but he used geometry for most of them to solve them. That's not how we would solve problems today. I guess at that time, mathematicians were more grounded in geometry than they were in algebra. So very different methods for solving these problems. And I think the methods presented in Principia Mathematica were a lot more cumbersome than the ones we would use today. But they were correct, as far as I know. I've never actually looked at this book, but I heard it's a very hard book to read and go through. For one thing, it's all written in Latin. So anyway, I'd rather not try to go through the Principia Mathematica. I just thought I'd mention it because it was a really groundbreaking textbook. Uh, anyway, yeah. Oh yeah, the last thing he did. I guess he became so famous after he published the Principia Mathematica. Probably rightfully so. I mean, I really think he was the greatest physicist of all time. He probably deserved all the fame he had, even though he did kind of ruin Leibniz, at least regarding calculus. Also he plagiarized his student Raphson, but other than that, he did do all this other stuff on his own, which I think puts him at number one in physics and the top five in math, like I said, of all time. But, he became master of the mint. I guess he was so revered, after the Principia that he became basically, a member of the Royal Society in England. And of course, England was a monarchy back then. You know, Queen had absolute power, I guess. I don't know who was Queen when he was alive. Uh, I don't think it was Queen Elizabeth. I'm not sure who it was, but I think it was a queen. And, one thing he did, he became master of the mint. And I learned this a long time ago. I think I learned this in a physics class I took. And our teacher, I don't know what his problem was, but I remember, I'll just tell you what he did first. So here's what he did. He was master of the mint. He wanted to make sure that the coins couldn't be counterfeit. They were very valuable coins. They were gold coins. This picture, these two coins on this picture, I believe, are gold coins. But he wanted to make sure that people couldn't counterfeit these coins. And so what he did was he put these, marks on the edges of the coin. You still see these today, I think. He put little, etchings, little grooves, on the ends, on the edge of the coin, so that it was very hard to duplicate that. Basically impossible for common people to do that in that time. And I actually had a physics teacher. I don't know why he said this. I'll never forget this. But this was when I was learning physics. I think I was in grad school. And I had some nutty physics teacher. And he mentioned, this is where I learned this from him. And he said, I don't know why he said this, but he said this was Newton's greatest accomplishment. Were these grooves on this coin. On these coins. I mean, come on. I don't know why the hell he thought that. Maybe because it saved Britain a lot of money in the 17th and 18th century, but they didn't have to worry about counterfeiting. So he might have saved the country a lot of money. But come on, I mean, it doesn't compare in my mind. I mean, I think this professor, whoever he was probably one of those money-hungry fools that John Denver was criticizing, and thank God I'm a country boy. So anyway, enough of that. But anyway, that completes my profile of Isaac Newton, one of the greatest mathematicians and physicists of all time. So thank you for watching. Long live math, and I'll see you guys next time. Bye.